In today's lecture, we are going to see the concept of Fermi surfaces. Actually, I think you have an idea of metal and different type of solids like insulator and semiconductor. And in my previous video, I have discussed the band theory of these solids. But the new idea about the study of metal is related to the concept of Fermi surfaces. So, I would like to start my today's lecture by a very important statement of a well-known scientist A.R. Magnetos. According to Magnetos, few people would define a metal as a solid with Fermi surface. Because whenever you ask any people what is metal, generally people say that metals are materials in in the atoms of whose in outermost orbit of whose atoms there are 1, 2 or 3 electrons. It means those materials are called metals which have valence electron either 1 or 2 or 3. This is a common definition of metal. But very few people know that a metal can be best defined in this manner, that metals are solids with Fermi surfaces. It means those solids which have Fermi surface, that is called a metal. This is a very deep definition of metal. Actually, when you say this, then this statement says that this may nevertheless be most meaningful definition of metal one can give today. It represents a profound advance in the understanding of why metals behaves as they do. The concept of Fermi surface, as developed by quantum physics, provides a precise explanation of the main physical properties of metals. So, from this statement, which I have noted down from the very important textbook on solid state physics by Kittel, that from this statement you have definitely understand that metals can be defined as a solid with Fermi surface, and taking these Fermi surfaces under account, you can deal with all the electrical properties of metals. Okay? And so this concept of Fermi surface is very important in discussing the physics of metals. Although we can find the Fermi surface of semiconductor too, but basically the idea of Fermi surface is used to discuss the physics of metals. Okay? Now in this first lecture on this Fermi surface, we will first of all see what is this Fermi surface and how it is constructed. Okay? In fact, when you talk about Fermi surface, this is the surface of a constant energy. And constant energy in which space? Actually, this Fermi surface is defined as a surface of constant energy epsilon f in k space, or you can say in momentum space. So if you imagine a surface in momentum space or k space, and energy is everywhere same on that surface will be called a Fermi surface. This is just like an equipotential surface, a surface where potential is everywhere same, okay? Or an ergodic surface, as you study in statistical mechanics, in particularly in case of microcanonical ensemble, where energy is same everywhere on the surface, in case of microcanonical ensemble. Just like that, if you think about not the physical space, not the position space or configuration space, but if you imagine a momentum space or k space, and in that space there is a surface on which everywhere energy is same, then that very surface is called a Fermi surface. Actually, when you talk about the metal, you know, in metals there are unfilled orbitals or unfilled energy levels. For example, you can see if we schematically show that this is a metallic specimen, and below this level all the energy levels or all the orbitals are completely filled, and above this the energy levels or orbitals are empty, not filled, unfilled. Then a surface at 0 Kelvin temperature, mark it, at 0 Kelvin temperature, a surface which separates the completely filled orbitals to the completely unfilled orbitals, or you can say the completely filled energy bands or energy levels to the completely unfilled energy levels. That very surface is called Fermi surface. So I have written here, you can see it separates the unfilled orbitals. When you say orbitals, that means energy levels, from the filled orbitals at absolute zero temperature. It means at 0 Kelvin temperature. Okay, and as I have told you that the electrical properties of the metal are determined by the volume and shape of the Fermi surface. This Fermi surface, what is the shape of this Fermi surface, what is its volume, that completely decides the electrical properties of the metals. Why this is responsible for the electrical property? The reason is that the current is due to changes in the occupancy of states near the Fermi surface. Because you know, whenever there will be a change in the occupation state or the occupied state of the metal near the Fermi surface, then electrical conductivity is caused. In fact, in equilibrium state, there is a particular configuration, particular number of electrons distributed in the surface. But due to any perturbation, if there is a change in that very number, then the changed value of occupation probability is responsible for the conductivity, because in that condition the electrons actually get flowed. Okay. So the electrical properties of metals are completely determined by the volume and the shape of the Fermi surface. Due to perturbation, actually there may be a change in the volume of the Fermi surface, or there may be if there is not a change in volume, there may be a change in shape, and due to that the occupation probability changes and the number of electrons in a particular volume gets changed, and so that the electrical conductivity arises. Okay, so this is what you say Fermi surface. So in nutshell, you can say that Fermi surface is a surface of constant energy in momentum space. Okay, and this surface separates the filled energy band to the unfilled energy band, or you can say that the filled orbitals or energy levels from the unfilled energy levels or orbitals at 0 Kelvin temperature. Okay. Now let us see how these Fermi surfaces are constructed. Actually, we construct the free electron Fermi surfaces from spheres of radius kf. When you say that kf is the radius of the sphere, it means you are talking about a sphere in k space, where we take this kf, which is actually the wave vector, and that as the radius of the sphere. Okay, and from this sphere in momentum space, we actually construct the Fermi surface. Okay. In fact, there are particularly two basic schemes for the construction of this Fermi surface. The first one is called reduced zone scheme. Okay, and what is this reduced zone scheme? What is done in this scheme? Let us see. Actually, in this reduced zone scheme, we select a wave vector uh, k, okay, of any Bloch function lying in the first Brillouin zone. So this k vector will lie in the first Brillouin zone. Such a wave vector is selected. And this procedure is known as mapping the band in the reduced zone scheme. It means this wave vector must lie inside the Brillouin zone. Okay. Now let us consider a Bloch function, and this is psi k dashed of r. And as it is a Bloch function, so you can express it as the plane wave modulated by this periodic function uk dashed of r. So psi k dashed of r is defined like this. This is e to the power iota k dash dot r times uk dashed of r. Okay. Actually here this k dashed is the wave vector outside of the first Brillouin zone, as you can see in this first figure. See here, actually in this first figure I have shown the first Brillouin zone of a square lattice of side A. Okay, you can see this is this dotted line, this dotted square represents the square lattice of side length A. Okay, and so you can say that this is equal to A. Okay, and this is also equal to A. And here I have noted kx on x-axis and ky on y-axis. And you can see this k dashed vector is outside of this first Brillouin zone. Okay, this is outside of the first Brillouin zone. Here there is in fact pi by a, okay, and this is minus pi by a. Okay, actually the wave vector k dashed can be carried into the first zone, forming the vector k dashed plus g, where g is the reciprocal lattice vector, and the wave vector at a point A, you can see this is on the zone boundary and is carried by g to the point A dashed. When you apply this reciprocal lattice vector g on this point A, then this is transformed to the point A dashed, and this A dashed also lies on the opposite boundary of the same zone. Okay, so here a question arises that shall we count both and A and A dash lying in the first zone? Answer is yes, because they can be connected by a reciprocal lattice vector, as you can see by this vector g. So we count them as one identical point on the same zone. Okay, but you can see that this wave vector k is inside this first Brillouin zone. Okay, but k dashed is outside of it. That has been shown in that figure 1. So I have written here that this k dashed is outside of the first zone, as we have shown in this figure 1. Okay. Now we can find the reciprocal lattice vector g such that k is equal to k dashed plus g, but this k is lying in the first Brillouin zone. Okay. Now let us substitute the value of k dashed from here. You can see this k dashed vector will be equal to k minus g. Okay, so let us put k minus g at the place of k dashed in RHS of this expression. Okay, so you can say that psi k dashed of r, this will be equal to e to the power iota k dash dot r uk dash of r. But k dash, you have seen that this is k minus g, so this is e to the power iota k minus g dot r times uk dash of r. Okay. Now let us simplify the RHS to some extent. You can see this RHS can be written as e to the power I k dot r times e to the power minus ig dot r times uk dash of r. Okay. And so this is e to the power ik dot r times uk of r. Why? Because this e to the power minus ig dot r times uk dash of r, this is actually equal to uk of r. Okay, here there will be k dashed. This is equal to uk of r, and therefore you can see this product e to the power ik dot r times uk of r. This is simply the Bloch function, okay, with wave vector k. So this can be written as it is equal to psi k of r. So you can see that psi k dash of r is equal to psi k of r. This is the reason that we simply say that although k dashed vector is outside of the first Brillouin zone, but the function psi k dash of r and psi k of r both are equal. Okay. So you can say that both e to the power minus ig dot r and uk dash of r are periodic in the crystal lattice. So uk of r is also when psi k r is of the Bloch form. Okay. Even with free electrons, it is useful to work in the reduced zone, as you can see in this figure number 2, where any energy epsilon k dashed for k dashed outside the first zone is equal on to an epsilon k in the first Brillouin zone, where k is equal to k dashed plus g. See the figure 2. Actually, in this figure 2, the energy wave vector relation epsilon k, you know, this is equal to h bar square k square over 2m. This is the relation between epsilon k and k. Okay, and this relation actually defines the energy of a free electron. Okay, so this has been drawn here. This curve, you can see that this a dashed represents this epsilon k, graphical plot of epsilon k in against of k. Okay, and this has been actually drawn in by the reduced zone scheme. Actually, this construction often gives a useful idea of overall appearance of the band structure of crystal. The branch AC, if displaced by, let us say, minus 2 pi by a, this is your branch AC, you can see, if this branch will be displaced by minus 2 pi over a, then you will get the branch A dashed C. Okay, and if the branch A dash C is displaced by 2 pi by A, then gives the usual curve for the positive value of k, as you can see. Okay, so this, when this AC will be displaced by this much, you will get this curve, which is the usual curve for the free electron parabola. And when this will be actually displaced by 2 pi a by k, here this is pi by a, this is pi by a, so the distance between these two, a and a dashed, is 2 pi by a. Okay, so in fact a crystal potential will be introduce band gaps at the edges of the zone at a and a dashed. Okay, and at the center of the zone, that is at this point C, you can see the point C, when viewed in the extended zone scheme, falls at the edge of the second zone. Okay. So the overall width and the gross features of the band structure are often indicated properly by such a free electron bands in the reduced zone scheme. Okay. Now let us see that I have told you that any energy epsilon k dash for k dash outside the first zone is equal to an epsilon k in the first zone, where k is equal to k dash plus g. Okay. And this was all about the reduced zone scheme. Now we will see the another scheme for construction of the Fermi surface, and this is called periodic zone scheme. Actually, in case of periodic zone scheme, a given Brownian zone can be repeated periodically through all the wave vector space. Okay, and in this scheme, the energy epsilon k of a band is a periodic function in the reciprocal lattice. That means epsilon k is equal to this epsilon k will be equal to what? This will be equal to epsilon k dashed plus g. Okay. Here actually epsilon k dashed plus g is understood to refer the same energy band as epsilon k. Sorry, here there will be not k dashed, but that is simply k. So in fact epsilon k and epsilon k plus g both will be same, and therefore you can say that this energy epsilon k and the epsilon k plus g both represent the same energy band. Okay. Let us for example consider the energy band of a simple cubic lattice. Actually, when I have taught you the tight binding approximation, then you have seen in that very lecture that the energy of the electron after perturbation is epsilon k, and that is equal to minus alpha minus 2 gamma times cos kxa plus cos kya plus cos kza. This result I have shown in the discussion of tight binding approximation, and you have seen that this alpha and gamma are two parameters or two constants. Okay. Now one reciprocal lattice vector of the simple lattice is given by g equal to 2 pi over a I hat. Okay. So if we add this vector k, the only change in equation 3 will be what? If you add this g in k, it means k is replaced by k plus g. Then what will be the effect on this epsilon k? Now you can see. Actually adding g with k will change the value of kx, ky and kz by 2 pi by a. So in this condition, this cos kxa will now become cos kx plus 2 pi over a times a, and this is cos kxa plus 2 pi. But cos kxa plus 2 pi, this is simply cos kxa. So you can see that adding this vector g to the vector k does not change the value of this cos kxa, cos kya and cos kzj. And as the values of these three numbers will not change, so there will be no change in energy epsilon k. Okay. So I have written it is identically equal to cos Ka, and the energy is unchanged when the wave vector is increased by the reciprocal lattice vector. Okay. If you will increase the wave vector by reciprocal lattice vector, there will be no change in energy. And so that the energy is a periodic function of the wave vector. Okay. So this is all about the periodic zone scheme. So I think you have understand the two schemes of construction of this Fermi surfaces. But in our in our forthcoming lecture, we will see the construction of particular Fermi surfaces. That is the determination of Fermi surface of semiconductor, the cyclotron resonance method for determination of Fermi surface of metals, and we will also see the cyclotron resonance for metals. And in all these videos we will learn about the construction of Fermi surfaces. This was just an introductory lecture on Fermi surface, but the particular problem will be solved in our forthcoming videos. Okay, thank you very much.